You probably have looked at an image like this before, where you see these like railway tracks or train tracks lead into infinity and converge at a point in the image. But we all know that these train tracks are parallel in real life. What makes it appear that it's actually converging to a point in the image? Is this what gives us a sense of reality? Is that what gives us a sense of realism in the picture? Have you ever wondered how we use this fact unknowingly to actually estimate depth in the image? Can we give robots the same superpower as we have been doing forever? Let's dive right in to the world of vanishing points. Just a quick recap from the videos before. We had talked about how paintings got better. In this medieval painting, we see that there is no concept of change in perspective, which is as objects get farther away, they do not get smaller. That makes it a little trippy and it makes it a little hard for us to gauge the distances, and it does not mimic reality. In the later paintings like the Renaissance era, in this case Pietro Perugino's painting, we see that these beautiful leading lines which we see in real life actually help guide the viewer into the scene in 3 dimensions. We can effectively imagine the scene in 3 dimensions. So the question is, can we write a little bit of math to actually do this automatically so that our robots can do this and navigate in the world effectively? Let's discover the answer in the next 20 minutes or so. So vanishing points essentially come because depth gets compressed as we go farther away from the camera. What I mean by that is the distance between the train tracks is the same, right? Let's say it's like half a meter, right? So the number of pixels occupied by half a meter closer to you would be a lot more than that is farther away from you. In this extreme case, the tracks which are closer to us occupy, let's say, like some 200 pixels. And as you go farther away into the distance, in this particular case near the sunset here, it actually merges to a single point, which means that the distance between the 2 points is 0 at infinity. And that is what we call as the vanishing point. Because at infinity, the distance between the 2 points vanishes, which are actually parallel in the real world. Let's look at this with a cartoon example. So we have our camera plane, and we have equidistant distances on the ground plane, which is the floor, right? Remember the train tracks? So let's draw a simple line, and then we have these dots, and they get projected onto this image. If you don't know what I'm talking about with respect to projections, I would urge you to watch the previous video on camera models so that this fact becomes very clear. The way you would get the projection is you would draw a line from the camera center intersecting the camera plane and to the world point, and where the point intersects the camera plane, that's where it would get imaged. And you can clearly see that the distances are not equal, though they're equal in the ground plane, and this is what we talked about, depth compression, and the points actually get closer the farther away they get. Great. Let's do this for another parallel line, and this is what it would look like. And you can clearly see that as the points get farther and farther away in both the green line and the blue line, they intersect at a point in the image. Remember the train track image? It was intersecting somewhere in the middle, and that's what it would look like. And that's going to be denoted by this red color point. And if we draw the ray which passes through that also gives us a little bit of information which we will decipher in some time. And this point, which is the intersection of the two parallel line points at infinity, is called the vanishing point. So just to recap, 3D parallel lines meet at the same vanishing point in the image. Fun fact that this point doesn't actually have to be finite in the image. This can lie outside the image. And that's one thing. We'll see a couple of examples of that in a bit. The 3D ray which passes through the camera center and the vanishing point is parallel to these 3D lines in the world, right? And you will see why that is in a bit. And multiple different vanishing points can exist. because you can have multiple different parallel lines which have no link to each other in the real world. Awesome. So let's look at this with a real life example, and this is a picture I have taken where I work at WPI. So like we have these like square patterns on the floor, on the carpet, where we can actually like manually draw these lines, and this is going to be the vanishing point. We can do this for things which are perpendicular to this on the same carpet, and this is what it would look like. If we join these two vanishing points, which are obtained from the same plane but they are perpendicular to each other, we obtain this vanishing line of the horizon. So remember, we have two vanishing points, we connected them, and then we obtain something called the vanishing line. Awesome. But what does this vanishing line even tell us? For example, we know that this essentially is the horizon line, which essentially gives us the height of the camera. Since the horizon line is above the image half, I was actually lower pointing upwards. And you have seen this happen every day in everyday life, where you actually take a picture of the sunset on a beach. If you point the camera down, you will basically see more of the sea. If you point the camera up, you will see more of the sky. And that's exactly what we are seeing here. This tells us about the angle. I am tilted or pitched up because of the way the vanishing line is tilted. I am tilting or rolling towards the right because of the way it's tilted as well. So I know I am pitched up because the camera is tilted upwards, because the line is tilted upwards, and I'm tilted towards the right because the line is not horizontal and it's tilted towards the right. So what does this vanishing line tell us? Let's continue this discussion. So parallel 3D planes share the same vanishing line. So let's take the lines on the ceiling. We know that the ceiling is parallel to the floor. So let's do the same thing, and they lie on the same line. Not at the same exact point, but definitely on the same vanishing line, right? Let's take ones which are different, which are not parallel now, and they definitely have a different vanishing line. So different parallel planes produce different vanishing line. So that is an important fact for us to keep in mind. Just to recap, parallel lines in the world intersect on the same vanishing line, but different parallel planes produce different vanishing lines. So the question is now, how do we actually find this through math? Let's go through this. This is simple high school geometry. We take a line, which basically is one of those vanishing lines, and then we take two different points on this line. And again, remember, this is all on the image plane right now. I'm going to denote it as x1 and x2 with the pixel coordinates u1 v1 and u2 v2. Let the line be represented as ax plus by plus c is equal to 0. If I write this boldface L, that is just the coordinates or like the values of this a, b and c. So now we know that this point lies on that line. And the way you would do that is you would basically feed this values of u1 v1 into x and y in the ax plus by plus c equal to 0. The way you would write this in linear algebra is that you would take the dot product of the coordinates of the point along with the coefficients of the line, which is x1 transpose L is equal to 0, and the same thing happens for x2, which is x2 transpose L is equal to 0. And remember that here we have homogenized the values of the point, so we have appended it with a 1. And we are going to use this trick a lot in projective geometry. That 1 effectively refers to the fact that this point is being imaged on the focal plane. Beautiful. In basic linear algebra, we know that we can combine these two things because the values of the coefficients of the line L, A, B and C should be the same for both the points. So we can stack these things up and sort of solve it as a linear equation. So we'll stack it up this way, and this is going to be a 2 by 3 vector, and we want a 2 by 1 vector. So what we will essentially do is, we know that the coefficients of the line L, which in the bottom image is referred to as the x, which is like the independent variable. Sorry for the abuse in the notation. Is going to be derived as the null space of this matrix, which is the x1 transpose and x2 transpose thing. So in other words, we are going to obtain the coefficients of the line L as a cross product between x1 and x2. Note that the direction does matter. We are drawing the line from x1 to x2, so the cross product is going to go from x1 to x2. And recall that the cross product of vectors is 0 if they are parallel. So now to find the intersection of two lines, so that we can find this vanishing point, what we want to do is two 2D lines intersect at x. Let's call it a1u plus b1v plus c1 is equal to 0, and so on for a2u plus b2v plus c2 is equal to 0. We can easily write this like just like before. We have swapped the transpose, so it's L1 transpose x equal to 0 and L2 transpose x equal to 0. We know that x is the point of intersection which lies on both the lines. So we can write the same thing we were doing before, where we concatenate these two things and we do the same null space trick. The only thing is L and X are now swapped. So the point of intersection between these two lines is obtained as the cross product, just like before. The only thing is like we've swapped L and X. So in other words, the 2D point and a line are duals of each other, which means that the line joining 2 points is the cross product of the 2 points, and the point of intersection of the two 2D lines is the cross product of the 2 lines. So you switch the names and obtain the other, and it will remain the same. Another cool thing we can do, because these are duals of each other, is if you apply a transformation to one of the points, you can apply relevant related transformation to the lines as well, which is going to be inverse transpose in this particular case. And the transformation could be anything. Great. Let's start talking about the geometric interpretation right now. So we have the camera, we have any point, and we have the ray which passes through that. And the ray is in normalized coordinate units, which we have seen from the pinhole equation. The normalized coordinate units u hat will be basically inverse of k multiplied by that line equation u from the last video. I would urge you to watch the camera models video for this to be more clear. And we can write this for two different points. And the line between them is basically the cross product. Remember, just from the previous few seconds. So we are going to get the line which is the intersection between u1 hat and u2 hat, and we are going to just cross product the things together, and we are going to get that directly. Great. So now let's take the plane which intersects the optical center O and the 2 points which we have seen, or it cuts through the line. Essentially that will give us a 2D line on the image is essentially a 3D plane crossing through the camera center. Remember, we need it to be 3 points to be a plane. We will take one point as the camera center, and we'll basically take the 2 edge points where the line crosses the image, right? Or you can imagine you need like one line and 1 point for you to make a plane, and that's what we are doing here. So we are projecting this L hat onto this plane pi, which is the red color thing. And the plane normal is basically given as the cross product of these two vectors, because like we are doing the right-handed rule. So we will basically get the equation or like the coefficients for this plane as the coefficients of L hat, with instead of 1 it will be a 0 in this particular case, right? And this is what you will see on the image on the bottom as well. And we can do the same thing again. We can do this for another different line which we have seen before, and you can keep drawing these planes as we go along. The 2D lines on the image intersect at 2D point that corresponds to a 3D ray. Just to recap, we have these blue line and the red line, and they intersect, and we basically have the 3D ray which corresponds to the intersection point, which is perpendicular to the two plane normals which we are seeing in red and blue here. Great, let's continue this discussion with vanishing points like we saw before. So we know that we have two sets of parallel lines, one on each part of the ground, and these are perpendicular to each other. So we know that we want to find the intersection of these like lines. So these are the 4 red points. The easiest way to do this is through cross products like we've seen before. So let's write it out, and this is fairly simple. And to find the intersections of these parallel lines, which is going to be the red dots, we are going to do cross products again. This is fairly simple, and I would urge you to pause the video and sort of ponder on this for a second, because the cyclic order of this matters. And then to eventually find the vanishing line, which is the red line, we want to find the line which passes through both of these vanishing points. And again, that is done through another cross product, which is fairly simple. This is just a inception of cross products, which is great. And then we get the vanishing line. So now let's take a specific example. So now we know that we have the plane of the vanishing line because we are taking the intersection of the optical center to that of the vanishing line. That's the red color plane, which is shown as the red line on the right hand side. And the distance from that plane to the ground plane gives you the camera height. And this is a side view just to illustrate that example. Remember, we were intuitively seeing how the height of the camera was tilted up or down, or was it up and down? And this is how we were actually getting it. Now let's take another example, which you might have seen. You might be one of those people who thinks out of the box and why look at the railway tracks or train tracks head on? We can look at it from the side. Can I still apply the same math here? Right? Let's look at it. So you have two sets of parallel lines. Let's call it ABC1 and ABC2. Because they are parallel, they will share the first two coefficients. The point of intersection of these two parallel lines would essentially look like this. And you see that the last element is 0. Remember that we generally normalize because it's homogeneous coordinates. The last one has to be 1, so we divide it by the last number. But the problem is, because it's 0, you divide it, the point is not finite anymore. I told you a while ago that this point has to lie and has to be within the image or outside the image, but has to be finite. This is one of the special cases where it's actually not a finite point. And what happens is, in this case, we say the parallel lines, the intersection of these lines is at infinity, which means that the vanishing point is at infinity. Let's look at another illustration from another view of how this looks like. As you go farther and farther away from the point on the vertical axis here, you will see that the arrow actually starts moving away and away, right? And what is happening is, you will essentially reach infinity at one point because these are parallel, and you take the cross product and you have to divide by 0, right? So parallel lines, if seen square on, intersect at infinity, and a point at infinity is given by the coefficients in the image planes of B and A, and it's 0 in the last element. So this plane is essentially parallel to the image plane, right? And A and B in this particular case refers to the direction on this unit circle, which you are seeing, which is the plane, which is the gray plane, right? So it's a little weird to think about it, but a point at infinity corresponds to just a direction, because at infinity you lose sense of how far something is, right? All the points at infinity lie at the line at infinity, which is essentially this red color circle, right? Here the surface normal is parallel to the z-axis in this particular case. I want you to pause this slide and look at it a little more carefully, because the concept of line at infinity is a little weird, but it's very, very powerful. Just to quickly recap, when you look at parallel lines head on, they will intersect at a point at infinity. A point at infinity is a plane which is parallel to the image plane, and this refers to only the direction. The A and B coefficients refers to the direction, almost like polar coordinates, and all the points at infinity lie on this line, but the only thing is their direction is changing. And this plane is parallel to the z, its surface normal is parallel to the z-axis, which means that it's parallel to the plane of where you were taking the picture from. So quickly to recap, what are vanishing points? How do you find vanishing points? How do you find the horizon line? Does a vanishing point always have to be finite? See you next time. Take care. Bye-bye.